Yeah, so we started discussing the uh, the different requirements for why we have to model, and uh, and then we discussed some of uh, the different methods of modeling, right? So you can have finite difference models or finite element models, and so on. Then we started talking about this Laplace equation in the two dimensions. Dou square h by dou x square plus dou square h by dou y square equal to 0. This is the equation that we are very familiar with. We've already seen this during the earlier part of the semester, right? So now to solve this particular equation, I need two boundary conditions in x direction and y direction each, right? So basically total of four boundary conditions are needed. And this equation is represents a confined aquifer at steady state, which is homogeneous and isotropic, and where there are no sources and sinks. So these are the conditions under which this particular equation uh, is applicable to be solved. Now, so what we're going to do next is to solve this equation numerically. Okay, so you'll observe how the method works. Now, before we solve it, we'll do a quick recap of Taylor series expansion. I've done this multiple times in the semester. I'll do it one last time today, and then we will use this as the basis to continue. Okay, so remember this: f of x plus delta x equal to f of x. This is our Taylor series expansion, please remember, plus f prime x into delta x by 1 or 1 factorial, which is 1 of course, plus f double prime x into delta x square by 2 factorial, plus higher order terms of order delta x cube. Okay, so you can just keep extending it, plus f triple prime x delta x cube by 3 factorial, and so on and so forth. It just goes on. It's an infinite series. Okay, so now this is let's call this equation number 1, and then equation number 2 is f of x minus delta x, which is simply f of x minus f prime x into delta x by 1 factorial, plus f double prime x into delta x square by 2 factorial, minus order of delta x cube terms. Right, now this is a simple application of Taylor series expansion. I have just written out how to compute the function at a location x plus delta x if I know the value of f of x at location x, and of course the first derivative, second derivative, and so on and so forth. Right, now if I add these two equations, what happens is I will get, so if I add equation 1 plus equation 2, I get f of x plus delta x plus f of x minus delta x, that is my left hand side, equal to 2 times f of x. These two terms will cancel each other out because here it's plus f prime x and here it's minus f prime x, right? These two terms will add, and it will become plus f double prime x into delta x square. Okay, I should be more careful. I should say delta x, the whole thing squared. It's not delta x square, it is delta x squared. Okay, let's be more careful. We'll just put a parenthesis here. Okay. All right. And of course, all the higher order terms just get cancelled out. All done. Now, if I rearrange this equation, I will get f double prime x equal to, take this term and then collect all the terms on the left hand side, f of x plus delta x minus 2 times f of x plus f of x minus delta x, the whole thing divided by delta x square. Right? How did this 2 factorial and this 2 factorial disappear? 2 factorial is nothing but 2. So I had half plus half, so it became 1. So that's why this term does not have any coefficient. It is simply f double prime x into delta x whole square. So when I added the two equations, the delta x square divided by 2 factorial, I added it twice. So the 2 factorial disappeared. It just became 1. Okay. And then I just rearrange terms and I get this simple expression which looks like f double prime x equal to f of x plus delta x minus 2 times f of x plus f of x minus delta x divided by delta x square, right? So now this is what we've got um, uh, by applying Taylor series expansion and kind of rearranging the terms and just adding the two equations and so on. Okay, now let us go back to our Laplace equation. What do we have? I have dou square h by dou x square. Okay, now this dou square h by dou x square, what is it essentially? You can think of it as h double prime of x, right? Look at this next equation. Head is a function of x, right? F double prime x is nothing but h double prime x. H prime would be dou h by dou x. H double prime will be dou square h by dou x square, right? So you can very easily imagine that. So then can I write it like this? Dou square h by dou x square. This is my left hand side. Okay. So now I have to, using this, I am going to do this expression that I have on the right hand side. I'm going to use that as the basis to write an expression for the second derivative of h. Okay. This is what we are going to do. Okay. So let us keep that in mind. So what I'm going to do is I have drawn a series of boxes. Okay. Let us say this is the domain in which I'm interested in solving for the head. Okay. So these boxes go from I equal to 1, 2, 3, 4, 5 all the way to capital N. And then in the vertical direction, they go from j equal to 1, 2, 3 all the way to m, let us say. Okay, this is the domain that I have. I have divided up my domain. Remember when we spoke about finite difference method and finite element method, the first step was discretization, which means I have a domain. I break that domain up into smaller boxes. In the case of finite difference method, those will be rectangular boxes or maybe even square boxes, preferably square, but if it's rectangular, it's okay. In the case of finite element method, you can have any number of different shapes in finite element method, but typically people use triangular elements. We'll not worry about that. We are going to focus only on finite difference for now. Okay. So I have this Laplace equation. I'm trying to solve it numerically. I want to solve it over this particular domain. I have broken up this domain into these different boxes. Okay. And I have numbered the boxes. The columns are numbered from I equal to 1, 2, 3, 4 up to capital N. And the rows are numbered from j equal to 1, 2, 3 up to capital M. Okay. Now I am picking a particular box. Okay. This box has got, let's say it's some random box in the middle of this domain. This box is given by I comma j. Okay. This box, the location for that box is specified by I comma j. I comma j is the identity ID for this particular box. One box to the right of this, okay, will be called I plus 1 comma j. If this box is I comma j, then the next box will be I plus 1 comma j, the next box on the right. And the previous box on the left will be I minus 1 comma j. Okay. Similarly, if I look at the box above it, if I pick this box, it will be I comma j minus 1, and the box below will be called I comma j plus 1, right? So this box will be called I comma j minus 1, and this box will be called I comma j plus 1. Okay. I hope everybody is following along. If there are any doubts, please stop me right now with the nomenclature that we are using, right? All I have done is broken up the domain into a number of boxes, numbered those boxes as 1, 2, 3, 4 up to I equal to 1, 2, 3, 4 up to N, and j equal to 1, 2, 3, 4 up to M, capital M. Okay. Then I'm just picking up a random box in the middle, which I'm calling box number I comma j. The identity for that box is I comma j. The next box on the right hand side will be I plus 1 comma j. The box on the left hand side of that box will be I minus 1 comma j. The box above it will be I comma j minus 1, and the box below it will be called I comma j plus 1. Okay. So now what I'm going to do is just go back to our equation f double prime x equal to f of x plus delta x minus 2 times f of x plus f of x minus delta x divided by delta x square. Okay. So now can I say dou square h by dou x square is the same thing as my left hand side here. F double prime x is nothing but dou square h by dou x square, which is what my, remember what I'm trying to solve. This is the equation I'm trying to solve. Laplace equation dou square h by dou x square. Okay. Which is, let me write it. I'm going to say it is approximately equal to h of I plus 1 comma j minus 2 times h of I comma j plus h of I minus 1 comma j divided by delta x square. This is a numerical approximation. Dou square h by dou x square assumes that h is a continuous function, but I have broken up my domain into these discrete boxes, right? Inside each box, actually the head is supposed to be a continuous function, but I'm going to assume that inside each box, the head h remains constant. So I'm approximating the second derivative with this. What is I plus 1 comma j? It is x plus delta x, right? Look at this equation. F of x plus delta x is nothing but the head in the x plus delta x, which is the next box, which is I plus 1 comma j, minus 2 times f of x, minus 2 times f of x, which is the value of the head in this box, I comma j, plus h of I minus 1 comma j, which is the head in the previous box, f of x minus delta x, right? So I hope this is making sense. But I'm simply writing this equation in terms of h. That's all I'm doing. Okay, so it is h of I plus 1 comma j minus 2 times h of I comma j plus h of I minus 1 comma j divided by delta x square. Any questions before I move on? I don't want this to be a head scratcher. No questions at all? Everybody's on the same page? Okay, good. So now, using the same analogy, I can write dou square h by dou y square as approximately being equal to h of I comma j plus 1. What should my next value be? I am simply extending what I wrote for the x direction. I can do the same thing in the y direction also. I don't have to prove it again in y direction. If it's true in the x direction, it is true in the y direction, right? It will be minus 2 times h of I comma j plus h of I comma j minus 1 whole thing divided by delta y square. So far, so good. Anybody has any concerns, questions? How did I arrive at these two equations? The first equation is for the x direction. I plus 1 comma j 2 times I comma j plus I minus 1 comma j divided by delta x whole square. In the y direction, dou square h by dou y square is I comma j, h of I comma j plus 1 minus 2 times h of I comma j plus h of I comma j minus 1, the previous cell, divided by delta y square. So this is the setup. So basically what I have done is, my original equation was dou square h by dou x square plus dou square h by dou y square equal to 0. This was a partial differential equation. I have converted it into this new equation where the first term can be approximated by that I plus 1 comma j, I minus 1 comma j, whatever that I've written there. And the second term can be expressed by this I comma j plus 1, I comma j minus 1, and again 2 times minus 2 times h of I comma j. So this is a numerical approximation of this particular partial differential equation that we have. Okay. Now, remember that I have written this equation for some random cell I comma j. Okay. So let me just go to the next point. Okay. So what I have done is I have identified 5 cells. Okay. I comma j. So I'm just going to draw this something that looks like a 5 circles connected to each other by this kind of a, okay. So the circle at the center, let us call that the cell in the middle, I comma j. The circle to its right is I plus 1 comma j. The circle to the left of that I comma j is I minus 1 comma j. Similarly, I have I comma j minus 1 and I comma j plus 1 above and below this I comma j. So this is called the 5-point stencil. Okay. So I can move this stencil to any point within my domain, right? Let's just go back. If I keep it at this cell, okay, this will be I comma j. The next one will be I plus 1 comma j. The previous one will be I minus 1 comma j. The one above will be I comma j minus 1. The one below will be I comma j plus 1. I can move this anywhere inside my box, inside my domain. I keep it in a box, and that box will become I comma j, and the surrounding 4 boxes, one to the left, one to the right, one above and one below, they will become this I minus 1, I plus 1, j minus 1, j plus 1, and all of that. Okay, so this is called the 5-point stencil. 5-point because I have 5 cells, right? I comma j, I minus 1 comma j, I plus 1, j minus 1, j plus 1. Like these 5 points. Therefore, it's called a 5-point stencil because I can move this anywhere. Right? I can move it anywhere. A stencil is basically something that you can move around and do the same things again and again. Right? So basically, this 5-point stencil gives me the opportunity to simplify this problem into a simple approach that can be applied at any point. Okay, so what did I have as my last step? Dou square h by dou x square plus dou square h by, I'll write it again here maybe. Okay, so I had dou square h by dou x square plus dou square h by dou y square equal to 0. Okay, suppose I assume, or suppose I pick delta x such that it is equal to delta y. I can do that, right? I have the domain. I can break it up into n number of boxes in the x direction and m number of boxes in the y direction in such a way I can pick the number n and m, right? Remember, let's go back here. This capital N, which is the number of boxes in the x direction, and capital M, which is the number of boxes in the y direction, is my decision. I can decide anywhere, any number capital N, any number capital M. Suppose I pick n and m in such a way that my delta x is equal to delta y, which means the size of the box in the x direction is equal to the size of the box in the y direction. So it's not a rectangular box, but it's a square box. Okay, suppose I do that. What will happen? Then these two equations will be left, you'll be left with something like this: h of I plus 1 comma j minus 2 times h of I comma j plus h of I minus 1 comma j divided by delta x square. We'll just forget that for a minute. So this is my first term divided by delta x square. The second term will be h of I comma j plus 1 minus 2 times h of I comma j plus h of I comma j minus 1 divided by delta y square equal to 0. But now remember, delta x and delta y are equal. So I can just remove the denominator. The whole thing is gone. Then I get this very powerful equation, which is like this: h of I comma j equal to h of I plus 1 comma j plus h of I minus 1 comma j plus h of I comma j plus 1 plus h of I comma j minus 1 divided by 4. Now this is a very powerful equation and it can help us solve a lot of problems. Look at this. What is this equation telling us? That my head at any cell I comma j is simply the average of the value of head in the 4 surrounding neighbors. I plus 1 comma j, I minus 1 comma j, I comma j plus 1 and I comma j minus 1. I have 4 neighbors, right? Oh, sorry. I should have been a bit more careful. Just a second. Well, okay, anyway. So I have this minus 2 times h of I comma j appears twice in this equation. So when you add these two, it becomes minus 4 times h I comma j. So therefore, that 4, if I, and it's got a minus sign, so I take it to the other side and I get this expression. Is everybody clear about how I got this expression? Right? I had minus 2 hij and minus 2 hij occurring 2 times. So that's minus 4 hij. So because it's minus, I took it to the other side and then divided both sides by 4, I get this. So h of I comma j is simply the arithmetic mean of the head in the 4 neighboring cells, right? So this is the power of the 5-point stencil, right? It gives you a very simple equation. Now you may wonder that, is that all there is? If I know but I don't know the head in I plus 1 comma j, I minus 1 comma j, I comma j plus 1 and I comma j minus 1. If I don't know it, what is the point of knowing this? How will I be able to solve this? We will come to that stage. Okay. But right now, trust me, we have made progress by even coming to this point where we can say that the head at any point, any cell inside this domain is simply the average of the 4 neighboring cells, right? That's what this is saying. Of course, assuming that delta x and delta y are equal to each other, then I get this very powerful finding from this approach. Okay. So what we'll do is we will take a real example of how I can use this 5-point stencil. Okay. So I'm going to take a domain. Okay. And I break it up into, I've already set it up for you. Just take a look at this. I have this domain in which I have, let's say 1, 2, 3, 4 cells in the x direction, and 1, 2, 3, 4. Again, 4 cells in the y direction. And then I have, cells all along the boundary of this domain. And I have 4 internal cells inside the domain. I have deliberately written the numbering for those cells. I have written them in different colors. Okay, 1, 1, 2, 1, 3, 1, 4, 1, 1, 2, 1, 3, 1, 4, 2, 4, 3, 4, 4, 4, 4, 4, 3, and 4, 2. These values are the boundary values. Okay, so at the boundary, I know the head for this entire domain. Okay, some head is given. These are the values of the head at the boundary. So in between, these values that are written in green, this is 2, 2, 3, 2, 2, 3, 3, 3. These 4 values which are written in green ink, those are the unknowns. All the other values are provided, right? The values in blue that are surrounding this entire domain, the head. Okay, when I say the values are known, I mean the head at 1, 1, 2, 1, 3, 1, 4, 1, and so on. All those cells which are written in blue, at those cells, the head is known. The head is unknown at those 4 cells which are written in green. Okay, so that's what I'm trying to say. So the numbers in blue are boundary conditions. So the head value is known. And I need to solve for the numbers in green. which means I want to solve for the head at 2 comma 2, 3 comma 2, 2 comma 3, and 3 comma 3. So how do I go about this? Anybody has any thoughts? Anybody has any thoughts? How do I go about this? Nobody? Okay. So what we are going to do is we are going to do the simple 5-point stencil approach and try to solve for these 4 values. Now let me just go back and look at the equation. What did I have? I had I plus 1, I minus 1, j plus 1, j minus 1, and 4 times ij. That's what I had, right? So I'm going to go to this first cell, 2 comma 2. Remember, I only have 4 unknowns. Head at 2 comma 2, 3 comma 2, 2 comma 3, and 3 comma 3. Only in these 4 nodes or these 4 cells, the head is not known. In all other cells, the head is known. Okay. So I'm going to first write it for 2 comma 2. So this is what the equation is going to look like. I plus 1 comma j. For the cell 2 comma 2, I plus 1 is I comma j is 2 comma 2. So I plus 1 comma j is 3 comma 2. I minus 1 comma j is 1 comma 2. I comma j plus 1 is 2 comma 3. And I comma j minus 1 is 2 comma 1. Minus 4 times h of I comma j, which is 2 comma 2, equal to 0. Okay. I hope everybody is following along whatever I've written here. What have I done? I have simply replaced, if you go back to this previous cell in this equation, I have written it for a general case I comma j, right? Okay. So I have I plus 1, j plus 1, I minus 1, j minus 1, and I comma j in that equation. But if I come to a specific case where I'm writing it for cell number 2 comma 2, which means I comma j of I comma j is 2 comma 2. Then I plus 1 comma j will be 3 comma 2, and I minus 1 comma j will be 1 comma 2. The first 2 terms in that equation. I comma j plus 1 will be 2 comma 3, and I comma j minus 1 will be 2 comma 1. And minus 4 times h of I comma j is 4 times h of 2 comma 2 equal to 0. This is the equation that I had. So I've written this equation for cell number 2 comma 2. Okay. And then you will notice that in this equation, I have underlined 2 of the terms in red. What are those 2 values? H of I comma 2, which is this value, and h of 2 comma 1, which is this value. So in this equation, I have 3 comma 2, which is in green here, so it's unknown. 1 comma 2 has been underlined, and that is the boundary value. I know that value. 2 comma 3 is again over here in green, it's an unknown. 2 comma 1 is this value, which is the boundary condition. So this value is also known. 2 comma 2, this is my unknown anyway. So in this equation, there are 3 unknowns and then 2 knowns which have been underlined in red. Okay, 3 unknowns, 2 knowns. Okay, now I'm going to go to the next cell. Remember, I don't have to write this equation for all the boundary cells because for the boundary cells already this head is known. I only have to write this equation for 4 cells. Okay, now I'm going to write it for the next cell, 3 comma 2. So for this cell, so this is equation for 3 comma 2. 4 comma 2 is I plus 1 comma j. 2 comma 2 is I minus 1 comma j. 3 comma 3 is I comma j plus 1, and 3 comma 1 is I comma j minus 1. Minus 4 times h of 3 comma 2, which is I comma j, equal to 0. Again, I have underlined two terms. Those 2 terms are boundary values. 4 comma 2, that's the boundary value here. And then 3 comma 1, that's the boundary value here. The remaining 3 terms are the unknowns. Okay. So in this equation also, I have 2 knowns and 3 unknowns. Okay. Let's move on. Now I'll go to the next cell, 2 comma 3. And this equation is for cell number 2 comma 3. So here I have I plus 1 comma j 3 comma 3, I minus 1 comma j 1 comma 3, I comma j plus 1 2 comma 4, I comma j minus 1 2 comma 2, 4 times h of I comma j, which is 2 comma 3, equal to 0. Again, the two numbers that have been underlined are the values at the boundary for which the values are known, 1 comma 3 and 2 comma 4. And you can see that in the boundary you have these values which are known. Now I go to the last cell, 3 comma 3, right? Last unknown. For that I have this following equation: I plus 1 comma j is 4 comma 3, I minus 1 comma j is 2 comma 3, I comma j plus 1 is 3 comma 4, and I comma j minus 1 is 3 comma 2, and then minus 4 times h of ij, which is 3 comma 3, equal to 0. So now this is a very important set of 4 equations that I have written, okay, in which I have each equation has 3 unknowns and 2 knowns, okay, and the 2 knowns have been underlined in each case. Okay, now what I will do is I will write this in the form, okay, I'm just going to write this in, oops, sorry, in this form. Okay, I'll collect all the known terms with the underlined terms and put them in the left hand side, sorry, in the right hand side, and keep all the unknown terms on the left hand side. Okay, so let me try and write it like this. Just watch. Okay, minus 4 h of 2 comma 2. I just want to make sure I don't make a mistake. So plus h of 2 comma 3 plus h of, I think, 3 comma 2. Okay, 3 comma 2 equal to minus 4 equal to, on the right hand side it will be minus h of 1 comma 2 minus h of 2 comma 1, minus h 1 comma 2 minus h 2 comma 1. Actually the right hand side is you don't have to worry about it. Okay, next equation, we will take this, no, we'll take the 2 comma 3 equation. Okay, so here h of 2 comma 2 minus 4 h of 2 comma 3 plus h of 3 comma 3 equal to something, some term in the right hand side. Let's not worry about that. Okay, I don't want to waste the time just writing all of that again. Okay, now let's go to the next equation, which will be 3 comma 2, 3 comma 2. So it will be h of 2 comma 2 minus 4 h 3 comma 2, should have been a little bit more careful, plus h of 3 comma 3. Okay, plus h 3 comma 3 equal to some constant, all the knowns you go to the left hand side, and then finally the last term 3 comma 3. So I will write that as follows: 2 comma 3, 3 comma 2, h of 2 comma 3, 3 comma 2 plus h of 3 comma 2 minus 4 h, I think it will be 3 comma 3 equal to some constant. All the known terms have gone to the right hand side. Now if you look at this, the way, okay, I've actually messed up a little bit on the second line, but anyway, but bear with me. So can I write it like this? These are basically four equations, 1, 2, 3, 4, right? And how many unknowns? Four unknowns, four equations, totally solvable. Okay, but this is a simple example where I have deliberately taken just four unknowns. What if I had 10 unknowns, right? Or what if I had 20 unknowns? Then although you can say 20 equations, 20 unknowns, it's solvable. It's not solvable by hand. This equation, it's still possible to do it by hand and get the answer. But as soon as you start hitting bigger numbers, if you have 10 unknowns, 20 unknowns, 100 unknowns, 1000 unknowns, it is no longer solvable by hand. So as a general rule, we have to write it in the form of a matrix. Okay. So I will write it like this. Okay. So just watch what we do. So -4, 1, 1, 0. These are the coefficients of the terms. Okay. The terms will be h of 2 comma 2, h of 2 comma 3, h of 3 comma 2, h of 3 comma 3. Okay. So in the first equation, there is no term h of 3 comma 3. So therefore the coefficient for that is 0. Okay. The remaining terms have corresponding coefficient. 2 comma 2 has got a coefficient of -4. 2 comma 3 has a coefficient of 1. 3 comma 2 has a coefficient of 1. And 3 comma 3, as I said, does not have a term. Therefore its coefficient is 0. And then equal to whatever terms are there in the right hand side. I'm not going to write that. Okay. So each equation will have its own known values, which anyway, it's not, let's not worry about it. Okay. So now the second equation will be 1 -4 0 1. The next equation will be 1 -4 1 1 0 -4 1, and the last equation will be 0 1 1 -4. Okay. I mean, I no matter what I do, the diagonal terms will always be -4 -4 -4 -4. Okay. So anyway, so now, I mean, if we had been a little bit more careful, we could have, the order of equations, we could have got even a nicer looking matrix, but it doesn't matter really. Okay, let's not worry about that. Okay. Anyway, so now I have a 4 by 4 matrix and all the coefficients are known. H 2 comma 2, 2 comma 3, 3 comma 2, 3 comma 3. These are the unknowns. The right hand side, all of these terms are known. So I can simply solve this as A is this matrix dot H, which is the unknowns, equal to B, let us say, if you compute all the values in this vector. So H, the head will simply be equal to A inverse times B. So using the 5-point stencil method without doing any complicated, you know, although the equation is supposed to be some kind of a partial differential equation, I have boiled it down to a system of linear equations which can be solved. If the numbers are small, they can be solved by hand. But if not, I can easily set it up in a manner that allows me to solve this as a system of equations. All it matters now is that I have to invert that matrix and then I'm done. Once I invert that matrix, I multiply that by the vector B. I get the head values in each cell inside my domain. So this is a very powerful way in which we can simplify what looks like a complicated problem to start off with, right? I'm trying to solve a numerical equation, which is an approximation of my Laplace equation, right? Dou square h by dou x square plus dou square h by dou y square equal to 0. What looked like something very difficult, very complicated, has been broken down into a system of linear equations, which can be solved, and then we are done, right? So any questions on this before I move on? I'll be very surprised if there are no questions. Okay, which means nobody followed anything. Okay. Okay. All right. But anyway, seriously, no questions? Right. So now the problem boils down to how to efficiently solve this system of equations such that I can get the answer quickly. Now remember, if it's a 4 by 4 matrix, it's okay. You can do it more or less in a very quick way and so on and so forth. But if you want to really solve the system of equations very rapidly, very quickly, you need some kind of a sophisticated way of solving this. Okay, so there are many iterative tools available to help us solve this. Okay, so broadly speaking, there are two iterative methods. The first one is called the Jacobi iteration. Okay, so we will just look at two iterative methods. We're not going to spend a whole lot of time on this. Remember what we are trying to do. This is our 5-point stencil: I comma j, I plus 1 comma j, I minus 1 comma j, and then I comma j minus 1 and I comma j plus 1. These are our 5 points. So I'm going to write this equation, the Jacobi iterative method. Very simple. Okay, so what it does is it says I will use I comma j will be equal to I plus 1 comma j, I minus 1 comma j, I comma j plus 1, and I comma j minus 1, the whole thing divided by 4. Now, what happens is inverting a matrix is also not necessarily, you know, such a simple task. The larger the matrix, the more difficult it is to solve. The more difficult it is to invert the matrix, right? In the previous step, in the previous slide, we just said H is A inverse B. If it's a 4 by 4 matrix, inverting the matrix is pretty fast, pretty quick. But if you want to invert a 100 by 100 matrix or a 1000 by 1000 matrix or a million by million matrix for that matter, it becomes very challenging. It takes a lot of time to invert the matrix because so many computations are involved. So it might not always be easy, which is where these iterative methods come into being. Okay. So now what I'm going to do, please pay attention to this. It's a little tricky to understand. Um let us say that at each cell in this domain, right, I have I equal to 1 to I equal to n and j equal to 1, j equal to m. And I have the boundary values all within the domain. I have so many different cells at which I don't know the value. I don't know the head value. But what I can do is I use an iterative method in which I say, let me guess the head in those cells. Okay, let me guess it, and then I'll keep iterating such that if two successive iterations my answer doesn't change or doesn't change by much, then I will say, okay, you know what, this method has given me the right answer. Okay, so in other words, I have an iteration counter. So let us say it is counting the iteration in the cell I comma j. Let us say I'm in the m plus 1th iteration. Okay, now the small m is the counter of the iteration. I'm counting the number of iterations, 1, 2, 3, 4, and so on. So how do I get the value for the m plus 1th iteration? I simply take the value in all of these other cells at the mth iteration, okay, which means the previous iteration. So if I want to know the head value at a particular cell at the current iteration, I have to take the head values in all my four neighboring cells in the previous iteration, add them all up, divided by 4. That gives me the head value at that particular cell for the current iteration based on the previous iteration's value. So I make an initial guess, and then using that, I get a new iteration. And then I keep doing this until I find that h of I comma j at m plus 1 minus h of I comma j at m. I take the absolute value of this, right? Now this value for, I'm going to do this for all values of I comma j. I take the absolute value of the previous iterations head in uh, cell number I comma j and the value at head at that same cell in the current iteration. I take the difference between the previous iteration and the current iteration, take the absolute number, and find the value, the maximum value of this, uh, the difference between successive iteration for all values of I comma j. So this is going to be my error. I define the error between successive iterations as the maximum value between the head value in the current cell and the current iteration and the previous iteration for all the cells, and I take the maximum value. Okay, and I take the absolute value of this. Okay, so that I don't care about the sign of the error as long as the error is small. Okay, I don't care. So what I do is I keep repeating this iteration, keep repeating until this error, whatever I have defined, is less than my tolerance. Okay, I can define a tolerance value. I can say that as long as the head value, as the error value is more than 10 power minus 3 meters, let's say. I'm just giving a number. Okay, it could be anything, 10 power minus 3, 10 power minus 4. My tolerance could be 10 to the power minus 2 meters, or 10 to the power minus 3 meters, or 10 to the power minus 4 meters, whatever, any value. I decide some tolerance value. And using this tolerance value, I just keep checking how my error is changing as a function of iteration. After a certain number of iterations, if my error goes below this tolerance, whatever the tolerance is, I can set that tolerance. If that happens, stop iterating. Right? So my method is very simple. I set a tolerance before I start. Okay, and then I make an initial guess. And then this Jacobi iteration just keeps going from one iteration to the other, but it keeps checking how is the error changing. Is the error becoming smaller or not? The smaller it becomes, the better it is. And once the error falls below my tolerance, I can say stop iterating. Whatever I got in the previous iteration, that is my final answer. Okay. Now, obviously, the tolerance value, it's completely under your control. You can set any number. I said 10 power minus 2, 10 power minus 3. You can even set 10, or you can even set 10 power minus 1. The lesser the tolerance, or the larger the tolerance, the more error will be there in your computation. The smaller you make the tolerance, the closer the solution will be to the correct answer. Okay, so this is the Jacobi iteration method. So it's a very simple way of solving this system of equations. But again, that initial guess that I made, right? Initial guess, if it is very far from the correct answer, it will take a long time to come to the correct answer. Okay, because the Jacobi iteration method is a very simple method that uses this scheme for computing the heads in all the cells. Okay, so I think we don't have too much time after this. Okay, so the next method is called the Gauss-Seidel method. Maybe I'll just give you a reference to that. So it's called the Gauss-Seidel iteration. Now it is a little bit more sophisticated than the Jacobi iteration method. You can even look this up online, how the Jacobi iteration method is different from the Gauss-Seidel method. In any case, we'll discuss it in the next class. Okay, so the next class we'll work out this Gauss-Seidel iteration method. I have an Excel file that illustrates the difference between the Jacobi iteration and the Gauss-Seidel iteration also. So I'll show that again in the next class, which will help us to understand how these two methods are different from each other and which one is better in different circumstances. Okay, so I'll stop for now. do we have a plan on when we are presenting the final project? I have not heard any questions about the final project. I'm getting a little concerned. Is everybody confident about the final project? I don't know. Shall we present on November 14th? Is that okay for everybody? Is everybody okay with November 14th? Speak up, please. You'll have to unmute, Raish.
Sir, in the code there is like parameter, some parameter is there. So like which parameter we can change and which one should not be changed?
That depends on, you're free to change any parameter that you want, but you have to be able to justify whatever change you make.
Okay, like flow rate and that flow which is mentioned in the question that can't be changed now,
So
which is not mentioned that.
if it is exactly, so if the flow rate is mentioned, obviously you can't change that. Then you can only change other parameters. Parameters that can change your results without changing the basic stuff, right? Like you can't change the location of the, for example, in other problem, you can't change the location of the contamination. You can't say, I'll change where the contamination started. No, you can't do that, right? So you have to decide which parameter is is valid to change. You can't go ahead and change any parameter that you want. So you have to apply your brain. You have to apply your mind. I mean, you have to apply your mind and decide which parameter is appropriate to change given the particular problem. Yeah, Raish, please unmute if somebody wants to speak in the classroom. Yeah.
No, sir. No one's to speak, sir.
14th is fine. Okay, that's good. So please be ready, and I want everybody to be in the classroom on 14th. Okay, so that we can have a lively discussion. Okay, absolutely no excuses. Everybody has to be in the classroom on 14th. Okay, it's Children's Day. Anyway, right. Thank you very much. Take care. See you all on um, Friday. Yeah. Bye.